Alright, good morning class.
Morning.
How are you guys?
Good. Awesome.
Okay, I need your energy today, come on. Because we will be covering a new chapter which is created by a handsome guy. Okay, so DC generator is the chapter that we will be covering today. So, what is DC generator? Before understanding DC generator, we must first understand a principle created by a very smart and also handsome person, which is Faraday's law. Woo! Thank you.
Who is that?
Huh?
Who is that?
Who is what?
Who is Faraday?
Who is what? Me ah?
Oh.
Thanks bro. Okay, thanks. Okay, Faraday's law. Faraday's law of electromagnetic induction is basically the relation between the magnetic fields and also the electric current. So this principle actually works in many generators in the society today, which is being used to create energies to the renewable energy to supply the society today, and also electric motor, which Tesla used to create many cars. Now we can go into DC generator. First, can anyone give me idea about DC generator? What it do? What does it do? Come on, ideas, anyone?
To convert
DC
mechanical energy into electrical energy.
Nice! Oh my god, I haven't teach and you guys know it? Alright, so basically it converts mechanical energy into electrical energy. How? Basically by turning this coil. When you turn the coil, it induces a current which can be converted into energy and light up the bulb over here. So there is three principles that runs in this concept. The first one is basically Faraday's law of electromagnetic induction. Electromagnetic induction basically explains that when the armature or the coil is being rotated or a force is being applied to turn the coil, it will actually induce a current or EMF to the light bulb to make it light up. Other than that, we need to understand the calculation behind this concept. Calculation, please. Alright, the calculation behind this concept, which is created by me, we'll be covering this equation after a few more weeks. But now we will be going into the right hand and left hand rules next. Alright, so basically now we know that Faraday discovered that there's a left hand Fleming rule and also right hand Fleming rule. So left hand Fleming rule is basically used for electric generator. Used for electric motor. Electric motor, which is the motor used in cars nowadays. Electric motors actually use electric to actually convert into the motion, but we won't be covering that because we are looking at DC generator, which we will use our Fleming right hand rule. So more or less is just application. The DC generator is just an application to our society, and after today we will be covering more of DC generator, and tomorrow Mr. Lance will come into our class and have a nice talk with you guys. Alright? Thank you class.
Okay, good morning class.
Good morning.
Okay, so how are you guys doing?
Good.
Good? Okay, good. Okay, so today I'm going to explain about my law, Lenz law. Thank you, students. Okay, so today, Lenz's law. So what is Lenz's law? Lenz's law states that the induced current flows in a direction such that it opposes the change that produces it. Okay, so besides that, Newton's third law, it always obeys Newton's third law, because Newton's third law states that every action has a reaction which is equal but in opposite direction. Okay, so now I'm going to show you what I meant by stating that statement. Okay, so this is a solenoid with a bar of magnet. Okay, so this one, how to determine the direction of current is we use the right hand screw rule. So when this is north, this is south, it always opposes the change, right? Lenz's law. So when you go in, it opposes the change. When you want to come in, they say no. So they push you back outwards. How do you push it back outwards is when you have a north here and a south here. Because when you have a north here, you will create north-north force of repulsion, right? So this will be north and this will be south. So then you will use your right hand screw rule. Your thumb will be the direction of magnetic field, and your other fingers are the direction of current flow. So north, south, like that. So your direction of current will be downwards. Okay. So the galvanometer will deflect to the right. Okay. So yeah, this is how you use the right hand screw rule on a solenoid. Okay. So now I'm going to explain how to use how to determine the direction of current flow in a DC generator. Okay, so this is a DC generator. Okay, so same. This obeys Lenz's law too. So this is north, this is south. This is the conductor. Okay, this is the coil or the conductor. So in order for it to rotate, you need to actually imply a force. So this is the force that produces it. Let's say I spin it like that, then only it will start to rotate. So I will spin here, force. I'll apply a force here. So when you apply a force here, Lenz's law says that you have to oppose the change. So they will have to need a force that goes upwards to oppose the force which is downwards. So how do you get a force upwards is that this one you have to use Fleming's right hand rule. So your thumb represents the force. Your index finger represents your magnetic direction of magnetic field, and the middle finger represents the current flow. Okay, so this is north to south. This is north south. Current inwards. X is inwards. So inwards, north, south, and the force will go upwards. Can you see? Upwards. Yeah. So basically, that's how Lenz's law works. Okay. It always opposes the change which produces it. Okay. Thank you, guys.
Alright, class. Good morning again.
Morning.
Morning.
Okay. So how is the class yesterday with Mr. Lance?
Awesome.
Alright, hope you all learned something new. Okay, so basically, last night me and Mr. Lance are in the lab, and we found out how to actually increase the efficiency of the model. So by increasing the efficiency of the model, we can actually reduce the resistance so that there is more current flowing through the circuit. So there's less energy loss into the environment. And second of all, we can actually increase the magnetic field lines across the coils. How do we increase? First of all, is basically by using stronger magnets. It's easy. By using stronger magnets, you have more magnetic field lines, logics, and by using more magnetic field lines, the coil actually cuts more magnetic field lines than usual. That's why more EMF will be induced. Other than that, doing things under low temperature will also increase the efficiency. Why? Because less heat will be produced. Less heat, obviously less energy being lost to the environment, and it actually increases the efficiency of this whole model. Okay, so now you guys fully understand the DC generator. here we will have some questions given by Mr. Lance to you guys as an investigation.
Good morning, guys.
Morning.
Okay, so I'm gonna assign some work to you guys. Relation between flux versus time graph and EMS versus time graph. Okay, you have to explain how does this graph is obtained from the working principle of a DC generator. This job is assigned to Lim. Okay, can do it, Lim.
Okay.
Okay. Wait. No. Sorry. Melissa, you do it. You do it.
Yeah, sure.
Okay. The mathematical equations related to EMF of DC generator. Lim.
Yeah.
Okay. Sorry about mixing up the two of you. Okay. And the last one, short explanation on the EMF produced by two or more coil of DC generator, which is done by Qiao Teng. Okay.
Yes.
Okay. Yeah. That's about it, I guess. Okay. Thank you for the class today.
Alright, thank you. Bye. Alright, great. Now moving on to the next presenter, we will have Melissa.
Yes, sir.
Okay, you will be doing the graph presentation, am I right?
Yeah, you're right.
Alright, let's present now.
Alright. Okay, for my part, my question is that how does flux vs time graph related to EMF vs time graph? This is the first 5 diagram, which is a position of the conductor, and for this line, this arrow thingy, it stands for B field, which is the magnetic field. This is the normal line which is acting perpendicular to the conductor. For this position, there are no cutting of magnetic flux because it's in parallel. For this, there are cutting of magnetic flux because of the perpendicular direction. And this position is at the maximum flux. For this 1, 3, and 5, the magnitude of the flux is equal to 0. And for the second and fourth, the flux is maximum. And at this position, the last one, it will return to original position after a round, which is in clockwise direction. Okay, now I'll introduce you a new equation, which is the EMF equation. It's a negative change in magnetic flux against change in time, which is the rate of change in magnetic flux. Okay, what is the negative sign stand for? Lenz's law.
Alright, but can you further explain the equation?
Yeah, sure. Just like I mentioned, the negative is the Lenz's law, right? Then how about this part? This whole thing is the Faraday's law. I'm going to talk about this symbol is change in magnetic flux. I'm going to talk about the 3 graphs, which is change in magnetic flux against time, the rate of change in magnetic flux against time, and EMF against time. The first graph, it is in this shape because at B1 and B2, the change in the magnetic flux is at maximum because they intersect at the maximum point. And for A1, A2, and A3, the value is 0. For this, the gradient is positive and increasing. For this one, also is decreasing and positive also. And A3 is same as A1. For the second graph, it is the derivative of the first graph. And you get something like this. For the third graph, you get EMF against time because of this formula, which is negative of the second graph. And you will get the opposite side. It's kind of like a reflection. That's all for today. Thank you.
Alright, Lance, you'll be taking over.
Okay, thank you, Faraday. Okay, so the next work is the mathematical equation of EMF, which is assigned to Lim, right?
Yeah.
Okay, can you please explain to other students about
Okay.
EMF mathematical equation? Thank you.
So according to Melissa's presentation just now, the EMF is equal to the change in magnetic flux over change in time. So for one revolution of the conductor, total flux produced by all the poles is equal to the magnetic flux times the numbers of poles in the machine. And the time taken to complete one revolution is equal to 60 over the speed of armature in revolution per minute. Therefore, induced EMF of one conductor is equal to this equation. When the conductors are connected in series in each parallel path, it's equal to total number of armature conductor over number of parallel paths in the armature working. So the average EMF is equals to this equation, which I call P-zone over 60A. Yeah, thank you.
That's all. Bye bye. Alright.
Okay, so first, we all of us know that a DC generator produces direct current, and a motor produces alternating current. So, according to Faraday's law of electromagnetic induction, when a conductor moves in a magnetic field, it cuts magnetic lines of force due to which an EMF is induced in the conductor. And the magnitude of this depends on the rate of change of flux linkage with the conductor. So as you can see here, the first diagram shows that the position of this loop is actually in a vertical position, and that so when you connect the circuit and then moves and electricity pass through this whole circuit, the current can flow through the whole circuit, and this thing rotates clockwise, and current moves from A to B and to C, from C to D. So how you can derive this is by using Fleming's right-hand rule. The thumb indicates the direction of motion of the conductor, and the index indicates the direction of magnetic field from north pole to south pole, as you can see. So it's here, north to south. And the middle finger indicates the direction of flow of current through the conductor. So next up we have this, and after it has turned from vertical to horizontal, it turns to vertical again, but this time it has switched sides. As you can see here, it has turned from ABCD to DCBA. So at this position, the tangential motion of the sides of the loop is parallel to the flux lines of the field. So there's no flux cutting, and no current in loop. Therefore, there's no current in the loop. So at last, it has turned back into the horizontal position. So it's actually the opposite side of this, from ABCD to DCBA. So the current flows from D to C and from B to A. So as in conclusion, we can say that the tangential motion of the side of this loop is perpendicular to the flux lines. It's perpendicular, like this. So it's perpendicular. And the rate of flux cutting is maximum because this is actually because the position is actually the closest to both of the magnets. Yeah, so hence why we can conclude that this is how EMF is produced in a DC generator.
Okay.